Okay, so let's start today by talking a little bit more in detail about these electromagnetic waves, about this electromagnetic phenomenon. And the definition that I like to use is that an EM wave is just a form of energy that is the result of a variety of natural and man-made processes, such as light, electric current, or perhaps nuclear radiation. And in all of these examples, electromagnetic waves have been produced via the motion of a charged particle. The motion of these particles, like an electron or a proton, will cause the production of an electric field in space and a magnetic field in space, and these fields will be oscillating with respect to both position and time. And also, as shown in this diagram here, where you see that there's a blue oscillatory wave that represents the E field from the motion of a charged particle, and this red sine wave that represents the B field from the motion of a charged particle, or the magnetic field. These fields are perpendicular. These established fields, the electric field and the magnetic fields, are perpendicular to one another. And as the EM wave travels through space, as shown in this direction, maybe from the left-hand side of the screen to the right-hand side of the screen, so in this direction, we see that the E field and the B field are also perpendicular to the direction of wave travel. So we say that the E field, the B field, and the direction of travel are mutually orthogonal, which is one of the main characteristics of this electromagnetic wave, is that it consists of two parts, the E field, the B field. Those are both perpendicular to one another, meaning they have a 90-degree angle between them. And then that wave will move through space in a direction that is perpendicular to both the E field and the B field. Again, we call that condition mutual orthogonality. So in short, if we've got a charged particle and it experiences movement, it will produce EM radiation, or electromagnetic radiation. And this radiation is a wave that will move through space, and as it goes, it establishes an electric field and a magnetic field as it travels. By establishing these fields, radiation carries energy as it moves. It stores energy in the electric field, which is then transferred into the magnetic field, which then is transferred back into the electric field. And although we haven't done the math yet to prove that, it's pretty easy to observe in nature. Go outside, stand in the sun, and as visible light from the sun, which is one very common form of electromagnetic radiation, as that sunlight hits you, you will feel warmth on your skin as the energy that's stored in that electromagnetic radiation is imparted into you. And, we've all seen cats and dogs laying in the sunlight in a cold winter day, and that's just an example of the transfer of heat energy to the cat via the energy stored in the electromagnetic wave of the photon from light. So like an AC voltage or a current waveform, if we were to plot an EM wave, it's sinusoidal, or typically we'll use a cosine, and we'll be more formal about this later. But the EM wave will have an amplitude, how big it is. It will have a frequency, which means how fast those peaks occur as a function of time. And we use our same formulas that the frequency of a wave is just 1 over the period. But remember that this wave I described to you is also traveling through space, so I have to draw a second graph, and instead of time, it's got to be distance. In this case, we'll call it meters. And it's also going to be oscillating in terms of distance, and so we still have this amplitude associated with the wave, but now we have a distance between the two peaks. And this is called the wavelength. And the symbol for that is lambda. And so unlike the classical description of a voltage and current, which is instantaneous across space, the EM wave is moving, and therefore the EM wave also has this wavelength associated with it, which is the distance the wave will travel in one full cycle. So this is measured in meters, and it's a distance. It can be pretty easy to confuse wavelength and frequency, and really what you just need to remember for right now is that the wavelength is a distance measurement in meters, and frequency is a time measurement, typically in units of seconds. So this would be distance, units of meters, whereas frequency would be time in units of seconds. Well, frequency would actually be hertz, right? Inverse time. In all electromagnetic waves, there is a relationship between the speed at which this wave is going to be traveling and the speed of light and the properties of the material in which the wave is traveling. And we call the speed at which the wave moves through space the propagation velocity, and that is mu sub p, propagation velocity. And propagation velocity, which is measured in meters per second, it's a velocity. It's got a magnitude and a direction associated with it, a speed and a direction. It's equal to the speed of light, which is a universal constant, 3 times 10 to the 8th meters per second. And the speed of light is then divided by a material property, which is called the relative permittivity, which we'll talk a lot more about in the class. And it's unitless. There's no units to relative permittivity, because you can see that we would divide meters per second by a unitless quantity to get meters per second. And from this equation, we see that the propagation velocity of an electromagnetic wave in a material is equal to the speed of light as measured in free space, so this is if a photon is moving through a vacuum, divided by the square root of what's called the relative electric permittivity of the material that the wave is traveling in. And again, we'll talk more about this relative permittivity later, but what's important right now is that an electromagnetic wave, like light, will travel at the speed of light in a vacuum or in free space, but the propagation velocity will decrease as that electromagnetic wave travels in a material. That material could be anything. It could be copper, it could be aluminum. If we're talking about electric circuits, it could be glass or plastic or water. If we're talking about optical electromagnetic, it could be human tissue. These waves travel through them, but at some specific speed, the propagation velocity. We can relate propagation velocity, wavelength, and frequency of an electromagnetic wave through a very specific formula, and that is wavelength is equal to propagation velocity of the wave divided by the frequency. So we've got wavelength in meters is equal to propagation velocity in meters per second divided by frequency in hertz, which again is just 1/seconds. Additionally, as I said earlier, there's energy stored in an electromagnetic wave, and there's a very simple way to calculate the amount of energy that is being transferred by an electromagnetic wave, and it turns out that that's only dependent on the frequency of the wave. And the formula for that is the energy stored in an electromagnetic wave is equal to h times the frequency. Well, what is this h? Because energy makes sense. You've seen that before. That's units of joules. Frequency, that's units of hertz. Well, what possibly could this h be? Well, it turns out that h is a universal constant. It's called Planck's constant. Some people pronounce it Planck. I think he was German. I'm not 100% sure, but that's Planck's constant. You may have seen it in physics classes before, and its value is constant, and it's equal to 6.626 times 10 to the minus 34 joule seconds. And so you can see that if we take a joule second, we multiply it by a hertz, which is 1/seconds, we're left with just joules there. So some very important relationships we've just described here for wavelength, propagation velocity, frequency, and energy, Planck's constant, and frequency, which are kind of the fundamental relationships that govern the electromagnetic phenomena.